Okay, we were right here in the last video. So this line is very important in this graph. Although, as you're going to see in the next slide, this graph is that we have a nice table to look up this information. So you don't have to sit there and say, all right, the temperature is 10 degrees Celsius. What would be the maximum specific humidity? And by the way, that's in grams of grams of water per kilogram of air. All right. Anyhow, so when the evaporation rate is equal to the condensation rate, the relative humidity is 100%. Again, that's this line right here. When the evaporation exceeds the condensation rate, all right. So that we're down here. So, you're below the saturation rate. Basically, all that means if you're in this area of the graph, that just means that the relative humidity is something less than 100%. It'll be less, right? If the condensation rate exceeds the evaporation rate, so you're up here in this area here, then the air is what's called supersaturated, and so the water droplets will form. It doesn't mean it's going to rain yet. That's actually a little bit more complicated. We'll get to that shortly. All right. So as I said, this graph here is summarized, at least somewhat anyway, in this table. All right. So you would, let's say the temperature was 0, to find the maximum specific humidity, that you just look it up. In between, you're gonna have to estimate. So let's say it was 3 degrees Celsius. So it's going to be the value of the maximum specific humidity will be somewhere between 4 and 5 roughly, right? So you can see that. All right. Well, let's see. Let me see something real quick. All right. So let's say that the dew point is reached, and of course that happens when the temperature of the air is when the dew point is the temperature at which the air is saturated. All right. That is, it can't hold any more water. All right, and so during that time, you get condensation, right? So when condensation occurs, you've reached the dew point, and water vapor begins to condense. If it's high in the atmosphere, you have a cloud. If it's lower to the ground, you get fog, or you get, that's actually what the early morning dew is. Sometimes you'll wake up and the grass will seem wet, and all that is the water vapor condensing on the ground, right? Of course, if it's cold enough, you'll get frost, and as I mentioned, I'm sure you've experienced fog before. So that's the condensation. And remember, we're not talking. It's not raining yet. We'll get to that shortly. All right. So the dew point can be used to indicate the water vapor content. High dew point, you get high water vapor content. Low dew point, you got low water vapor content. And remember, as far as temperature goes, higher temperature, like if you think of an air parcel of some region of air above the ground. If the temperature is greater, the water vapor content can be greater. If the temperature is lower, the water vapor content is lower. All right, so let's keep going. The dew point is always less than or equal to the air temperature. Right? It can't possibly be greater. All right, so the dew point is always less than or equal to the air temperature. And then, of course, when it's equal, that's when you have condensation occurring. All All right, so the difference between the air temperature and the dew point is used to indicate the relative humidity. All right, whether it's low or high. If you have a big difference between the dew point and the outside temperature, then that's really low humidity. All right, because of course the dew point is always less than the temperature, or equal to. Okay, but if it's equal to, that's you're not talking about low humidity. When the dew point and the temperature are close together, or the same number, that's when you have high relative humidity, right? So when it feels very muggy out, that's high humidity, and of course the dew point, which is a certain temperature where condensation can occur. All right. Let's see. Is the air temperature? I'm sorry. As the air temperature increases, what happens to the relative humidity? If the air temperature goes up, the relative humidity will definitely go down, because you can put more moisture into the air at higher temperatures. All right. So. All right, there it is. So it says as temperature increases, the air is able to accommodate more water vapor. The water vapor capacity is increased, all right, and the relative humidity decreases. All right, very nice. When the dew point is high, what happens to the relative humidity? Okay, so when the dew point is high, then that means that the relative humidity is really high, right? Okay, so yeah, relative humidity. So the dew point is the temperature at which the air must be cooled to become saturated. A high dew point indicates that there's a lot of water there's a lot of water content in the air, right? And so you don't have to decrease the temperature all that much for you to really feel that water. Remember, there's always water in the atmosphere. It's just the relative amount. That's what we're talking about, the relative humidity. All right, air pressure. Okay, so pressure is force per area, the amount of force per area. So the force exerted by the movement of air molecules on one another. The faster the air molecules are moving, the greater the kinetic energy, and therefore the greater the air pressure. So warm air exerts a higher air pressure on its surroundings than cooler air. Right? So keep that in mind as we're going through this. These things, the temperature, pressure, and the density of the air molecules, they all contribute to what's going on with the variables, the weather variables, right? Those literally are the variables that go into the weather. Although we're going to see some other things in just a moment. Let's see. So the denser air, the denser the air is, the more molecular collisions, and so you get, with more molecular collisions, you get higher pressure. Air pressure, density, and temperature are definitely interrelated. All right. So here comes a concept from. This is actually from the area called thermodynamics. So if you have an adiabatic process, all that means is no heat was entered into the system or taken out of the system, right? So adiabatic processes occur when air is either expanded or compressed, but there's no heat exchanged, right? So and there's a really good example. Let's see, do they have that? No. There's a really good experiment that you can perform. It's really simple, right? So you just hold your hand really close to your mouth, and you I don't know if you can hear me doing this. You just kind of blow on your hand, your open palm. You just blow on it with your mouth just, open wide. So you just go like that, kind of a ha, like that. All right. And so you can feel the hot air, on your hand. Okay. So the air has not expanded, right? It's just simply gone out of your mouth, and it is not expanded at all. If you put your lips together, kind of like you're about to whistle, and then you blow, the air, and keep your hand the same distance away from your mouth. So, it's the same temperature coming out of your mouth, but the air has expanded a little bit and it feels cooler. I mean, try it. You can definitely, just blow on your palm, right, with your lips close together, and it definitely feels cooler. So that's an adiabatic process, right? There's no exchange. There hasn't been enough time, basically, for the air that's coming out of your mouth to change temperatures, right? That doesn't have enough time to do that. So it's really just the compression of the air that is cooling it. All right, very nice. So adiabatic expansion, and the temperature of dry air, so unsaturated air. You have an air parcel. So this is what they call adiabatic lapse rate. All right. So the adiabatic lapse rate is roughly 10 degrees per kilometer for basically dry air rising. Right. So dry air, as long as it stays dry and unsaturated, as it goes up, every kilometer, the temperature will decrease by 10 degrees. All right, but that's not always going to be the case. Let's see. Oh, this is so here. This is what's called a Chinook. People who live in the Rockies experience this. So when you have warm, dry winds that occur after, so let's say you have cool, moist air rising up over a mountain, as it's shown here, as it goes down the mountain with where there's no heat exchange going on. That's the adiabatic process, right? What's happening is, as this cool air goes down the mountain, it's, the pressure down here is greater, and the air gets compressed and warms up. It warms up, and that's called a Chinook wind. All right, so I think that's a Native American term. All right, let's see. So the adiabatic process also occurs with moist air, and of course we're going to have this moist air adiabatic lapse rate, which is a little bit less than, remember, for dry air, the temperature decreases 10 degrees per kilometer of altitude. But here, because the air is moist, and there's condensation going on, and see, that's the thing. Condensation releases heat. It's the process of condensation will release heat to the surroundings, and so when moist air rises, you still have a decrease in temperature, but it's only roughly 6 degrees per kilometer rise. So that's moist air, or moist adiabatic lapse. That's called the moist adiabatic lapse rate. 6 degrees per kilometer rise. All right. Anyhow, so under normal conditions, air temperature, it's the normal thing that we think of. Air temperature decreases with altitude, right? I mean, that's a pretty standard thing. This rate of cooling varies from place to place and can vary even over the course of a day. All right. So it gets a new term, an entirely new term, because different things are going on. So it's called the environmental lapse rate. I know it's a little confusing, but it's the rate at which the air cools, per increase in altitude. And on average, okay, so it varies, but on average, this environmental lapse rate is about